Such a pleasure to have you with us here today. Uh, Let me uh, introduce the fantastic work that Professor Bob has been doing. Uh, Robert Herman is his full name. So, Professor Bob Herman is the professor in the Department of Physics and Astronomy at Ohio Wesleyan University. He earned the BS in summa cum laude in astronomy at Case Western Reserve University and then went on to earn a MS and PhD in physics at the University of Chicago, where he won the Gregory Wenzel Prize for the best first year graduate teaching assistant. Before coming to Ohio Wesleyan, which is also known as OWU, in 1999, Professor Herman taught at Washington College and Randolph-Macon College, and he was a visiting researcher at the Harvard Smithsonian Center for Astrophysics. In addition to teaching courses in theoretical physics and in theoretical and observational astrophysics, he utilizes OWU's Perkins Observatory for classes and research, including the study of star spots. He mentors undergraduates conducting research during the summer, the results of which are often published and presented at regional and national conferences. Once again, Professor Bob, it's such a pleasure having you with here today, and we look forward to learning and sort of exploring the world of astrophysics.
It's a pleasure to be with all of you.
Superb. So we'll straight away jump into the questions. And my first question to you is, how do you explain astrophysics to a high school student who is curious about stars and space, but doesn't know where to begin?
Yeah, there are a lot of good books out there for sure. One that I particularly recommend is actually a textbook called Astronomy 2E from what's known as the OpenStax project. And the nice thing about it is that it's completely free. You can read it online. You can also download a PDF of it. It's used, its target is sort of astronomy 101 courses in colleges. But it's also used in high schools. And I think that a group of smart students like yourselves would certainly have no trouble handling it. So I think that's a good place to begin if you want a broad overview of topics in astronomy and astrophysics. I will put a link later in the chat that has a document that I've shared with everybody that you can click links on it and get to all the resources that I'll be mentioning today. There's also a video series that I like a lot called Crash Course Astronomy. Astronomer Phil Plait made 46 videos, which are a video version of sort of an Astronomy 101 course. There's 46 of them. I use a lot of them when I'm teaching because I tell my students that he has special effects and so forth that I can't create in the air behind me. And so I think that's a good place to go too. There's also PBS Spacetime, which is a channel on YouTube. The videos tend to be at a bit higher level than those in Crash Course Astronomy. But again, at the same time, even though he might be mentioning the equations of general relativity and so forth and actually show them to you, you can get a lot out of the videos, whether or not you're trying to follow along with the math. And someday you will be able to follow along with the math, which I think is exciting.
Fantastic. Thank you so much. So we got three things: astronomy 2E, and there is a
Hmm.
crash course on astronomy, and then there is a space-time YouTube channel. And
Yep, PBS Spacetime. Yep.
okay, and I'll request you to share the link maybe towards the end of the session so that students can delve deeper and sort of satisfy their curiosity on astronomy. So, Professor Bob, why is astronomy and astrophysics important in everyday life? How does it help us with the navigation, with the satellite, and also with climate sciences?
Yeah. So one thing I'll say is that it's certainly not the case that a typical person in their everyday life is sort of using astronomy in detail. But on the other hand, it's in the background in so many things that are very important to all of us. So our modern high-tech society absolutely relies on satellites, GPS and so forth. So one example I could give where knowledge of astrophysics is important to our society is space weather. So the sun has a powerful magnetic field. In fact, it's one of my particular interests and stores a lot of energy. And when that energy is released suddenly, we can get things like solar flares and coronal mass ejections, where millions of tons of charged particles are shot out into interplanetary space. And when those impact Earth's magnetosphere, then we get cool things like auroral displays. I recently saw some very nice auroral displays here in central Ohio. But they also have the potential to cause a tremendous amount of damage to satellites, to power grids on the ground, and so forth. And understanding better the sun's magnetic field and space weather and so forth is important to prepare ourselves to harden our technological infrastructure and so forth to predict what's coming. That's something that there are astrophysicists who make that their field of research. Um, you may have heard that gravity is curvature of space-time according to general relativity. Not that gravity causes curvature of space-time, it really is curvature of space-time. And you may also know that if you got close to the event horizon of a black hole, time would slow down as seen by people from the outside. And at first, that seems like something that's just very esoteric, something that wouldn't ever have a practical application. But that so-called gravitational time dilation applies to all gravitational fields. We'd never measure it, but your body is slowing down time a little bit, closer to you than away from it. Earth does the same thing, not nearly as strongly as a black hole does. But when Einstein formulated general relativity, at first it seemed like this is fascinating, it's revolutionary, but it'll never have any practical applications. But it does, because global positioning satellites work by having your receiver get signals, radio signals from multiple satellites, and those are time-stamped with when the signal was sent and with the location of the satellite. And your GPS receiver, like your phone or whatever type of receiver you have, triangulates its position on Earth from those signals. Light travels 1 meter in just 3 billionths of a second, 3 nanoseconds. And that means you need very precise timing in order to get GPS to work. And it turns out that if you did not account for the general relativistic gravitational time dilation of the satellites that are higher up above Earth's surface than we are in Earth's gravitational field, GPS simply would not work. And so, what seemed at first like something that was fascinating but would never have practical applications is now worth billions and billions of dollars to the world economy. And it's something that most people, I think, use every day, or at least very often, as far as that's concerned. Climate science, in order to understand global warming, in order to understand the so-called atmospheric greenhouse effect. That is radiation transfer. And that's something that astronomers need to learn in order to understand how stars work. And so I'm teaching Astronomy 310 this past semester. And so I'm teaching my astrophysics students about radiative transfer and applying it to Earth's atmosphere. It's something that some of them may go on to do professionally. I have a former student who was an astrophysics major. Now he's a climate scientist, for example. So I could go on and on, but there's lots of examples like that. Although I will say, uh, the best thing about astrophysics is that it gives us the big picture. It gives us our place in the universe. And that's my real motivation for doing it. And then it's wonderful that there's also practical effects as well.
Fantastic. And Professor Bob, I would love to know a little more about how you got excited about astrophysics in your, when did that spark come in that this is what I want to do?
Yeah, you know what? It actually happened when I was a little kid. I can't remember exactly how old I was, but I was probably about 7 or 8 years old. And my dad had a series of books called the Time Life Nature Library, and one of them was called The Universe. And one day he showed me a painting in it that was representing the sun and the planets to scale. Now, you can't put their distances from one another to scale at the same in the same painting that you would show the planets themselves, their sizes, but it showed the sun and all the planets, how big they were relative to one another. And he said to me, which one of these do you think is the Earth? And I could see for myself, so to speak, that Earth is way bigger than all those little dots in the sky and so forth. And so I pointed to the biggest object in the painting. That had to be Earth. And he goes, that's actually the sun. And my jaw kind of drops, like, what? And so then he says, do you want to try again? And I said, okay. And so I pointed to the second biggest object in the painting. And I'll bet all of you are thinking, oh, then you pointed to Jupiter. And that's absolutely right. And he goes, no, that's actually the planet Jupiter. My jaw drops again. And he says, do you want to try again? And I said, no, Daddy, you just tell me. And so he pointed to what Carl Sagan later called the pale blue dot that was Earth. And I was just absolutely floored that what I was living on was so small compared to many other things. And that was my epiphany, if you will. I became so interested in learning all about it. I wish I still had them, but I would read, once I could read, I'd read books about the solar system and then write my own little books about the solar system, for example. Don't have them anymore. I wish I did. But I was fortunate to know from when I was a little kid that I wanted to learn all about the universe.
Wow, such a fantastic story, and I'm sure with conversations like these, I think that we get that spark that okay, this is what I want to learn, this is what I want to study and do. Uh, in the foreseeable future. I don't say all my life, but at least in the foreseeable future. So, Professor Bob, technology is evolving fast. How are these new technologies like AI, robotics, advanced telescopes, etc., changing the way that scientists see the universe?
Yeah, they're profoundly changing it. So, it used to be that typically astronomers would photograph in the old days, get CCD images, digital camera images now of individual astronomical objects like a star cluster or a galaxy. And so, for example, back in the late 1960s, Vera Rubin and Kent Ford used, it turns out, a telescope that at the time belonged to Ohio Wesleyan. They weren't at Ohio Wesleyan, but they used a telescope that belonged to Ohio Wesleyan to observe star forming regions in the nearest large galaxy to ours, the Andromeda Galaxy, and measure how fast they were moving in their orbits around the center of the galaxy. And what they discovered is they're moving faster than you would expect if the only gravity that was available was the combined gravity of all the stars and gas and dust in the galaxy. And later on, Vera Rubin went on to study many more galaxies and the interpretation of that, and some of you may have heard of this, is that most of the matter in the universe, it turns out, is what we call dark matter. It doesn't emit or absorb or reflect light, so we can't see it. And it seems to be some sort of exotic new particle that we haven't discovered yet. There's a Nobel Prize waiting for whoever can find it. There's more than 5 times as much of that as there is the baryonic matter that stars and galaxies and people, protons, neutrons, electrons are made of. There's still a role for that kind of work, but now, speaking of Vera Rubin, for example, we have coming online the Vera Rubin Observatory on a mountaintop in the desert in Chile. And it has, your phone might have a 12 megapixel camera. Some of them have 200 megapixel cameras, although it's usually binned down to much less than that. The Vera Rubin Observatory has a 3200 megapixel camera. And for the next 10 years, it's going to be making photographs, digital photos of the entire southern portion of the sky, producing petabytes of data. A petabyte is almost 10 quadrillion bits of data. There's so much data coming from Vera Rubin and from other projects. We're in the age of big data now. It's too much for humans to handle. You just can't do it. And so it's astronomers now are very actively using neural networks, artificial intelligence, machine learning to help us process those reams of data. And so that has opened up new realms of discovery that simply wouldn't have been possible before these technologies existed.
Uh, I have a, it might be a stupid question, but James Webb Telescope is out there, right? I always imagined that it would be in some place in the US or on the ground, but that's not the case. Like, why do we put telescopes out there in the space and not place them on Earth?
Yeah, so first of all, I will say that's not a stupid question at all. One thing I always tell my students is the only stupid question is the one that you do not ask. And also, in class, students I think often will think, oh, I bet everybody else knows the answer to this, and I shouldn't ask this question. And I always reassure them, whatever question you ask, there's somebody else in the class who's like, you're my hero. I was thinking the same thing, but I didn't want to ask it. But in any case, no, that's a great question. And the reason we do that is because, well, astronomers have kind of a love-hate relationship with our atmosphere. We appreciate the oxygen, but at the same time, it blurs stellar images, and it only lets a narrow range of electromagnetic wavelengths. Light is a form of electromagnetic radiation, electric and magnetic fields traveling through space together. We can only see a narrow range of visible light, what's of course why we call it visible is that our eyes can detect it. But we learn so much about the universe by looking at all different wavelengths of the so-called electromagnetic spectrum. We can see radio waves on the ground. It wouldn't make sense to build a radio telescope in space. We can see visible light on the ground. It still makes sense to put telescopes in space because it gets you above the blurring effects of the atmosphere, the dimming effects of the atmosphere. And then there are infrared wavelengths, like, for example, the James Webb Space Telescope uses, and X-rays and gamma rays that simply don't penetrate the atmosphere. In the case of the X-rays and gamma rays, that's a good thing because they would kill us. If you went onto the surface of Mars, you would get a horrible sunburn within 30 seconds because of all the ultraviolet light reaching the surface that our atmosphere protects us from. So we need to put telescopes like James Webb in space in order for it to work in the first place, in order for it to see those wavelengths of light that simply don't make it to the ground through our atmosphere.
Wow, now I know. Now I know. Yes. Okay. So let's talk a little bit about your research. Could you share some examples from your own research where technology helped you uncover something new about stars and planets? And you can call it this was my aha moment. Yeah.
Yeah. Well, what I will say is that I'm involved in a NASA project right now. I have a NASA grant. And as an aside, I'll mention that it was very important to me and my collaborator, who's Rachel Rotenbacher, who graduated from Ohio Wesleyan back in 2008. She and I work on star spots. I got her interested in it when she was here, and we've collaborated ever since. Star spots are regions of strong magnetic field on other stars. On the sun, we call the star spots sunspots. That's part of the reason I'm so interested in the sun's magnetic field. The strong magnetic fields suppress convective transport, rising and sinking gas, convective transport of heat from deeper layers below. That makes them darker than the rest of the surface. Other stars are so far away that we can't directly photograph them like we can the sun, but we can detect the effects of the star spots. When the star is rotating, as the spots, the dark spots come in and out of view, the brightness of the star changes as a result. And I developed a computer program that can take those brightness variations and turn them into a rough map of the star spots. So where does the technology come in here? Well, of course, they're using the computer program, but in particular, the Kepler Space Telescope was launched in order to study exoplanets, planets orbiting other stars. When an exoplanet passes in front of its star, as seen from Earth, it blocks some of the star's light, and so the brightness of the star diminishes for a while. But star spots also cause brightness variations, and so the Kepler Space Telescope sort of accidentally, although they very much knew it would happen, discovered star spots on tens of thousands of stars. And what Rachel and I are involved in is systematically using my program to study the star spots on those stars. It'll be the largest study ever done of star spots in terms of the number of stars involved. That many stars, it's overwhelming to do what we need in order to process the data because it turns out that when you make a map of the surface this way, the noise in the data can cause all kinds of artifacts to appear on the surface of the star. And so we have to try different assumed amounts of noise, and you'll get reconstructions of the star surface that are covered with garbage artifacts, and others where those are gone and you can see the star spots. And it's not hard for a human to look at those and determine which ones are the good ones and which are the bad ones. But with tens of thousands of stars, it's overwhelming. It's too much. And so part of the money of the grant pays for two students to work with me every summer. And I'll mention that even though it's a NASA grant, you don't have to be a US citizen to participate. And so this summer, a student who is from Colombia, Isabella, she used a convolutional neural network using TensorFlow, which is free to download. I've got a link to that I'll share in that document. It's a machine learning program that anybody can download and play around with. It's a great way to learn about machine learning and actually apply it yourself. And so she made a convolutional neural network where she fed it lots of these reconstructed stellar surfaces and labeled some of them sort of, bad garbage and others good, and trained the neural network to do what humans do, which is sort of look at them and pick which ones are good and which ones are bad. And so I now have the opportunity to use machine learning in order to do research that I wouldn't be able to do without it.
Wow, fantastic. Thank you so much, Professor Bob. Now, let's talk a little bit about career paths. What kind of career paths can students explore in astronomy, astrophysics, um, and other technologies, related technologies in the years to come?
Yeah. So, of course, very often if somebody's studying astrophysics, they want to be an astrophysicist, an astronomer, an astrophysicist. As an aside, by the way, I'll say astronomy and astrophysics. And when I was an undergraduate at Case Western Reserve, one day one of my fellow astronomy majors and I asked our professor, "What's the difference between astronomy and astrophysics?" And the professor kind of made a joke that's always stuck with me, which is astrophysics sounds better when you're at a cocktail party. Um, Sort of unofficially, astronomy is the observational side, and astrophysics is the kind of theoretical computational side of it. But really, it's all, under the umbrella of astronomy. So folks that study astronomy and astrophysics, they often want to be a professional researcher. One way, of course, to do that is to become a professor, to get a faculty job. I will say that there are more people that would like to get a faculty job in astronomy than there are faculty jobs available. But there are other paths as well. So, for example, you can become a research scientist, is usually what it's called. That's actually what Rachel, my collaborator on the NASA project, is. She's a research scientist at the University of Michigan, where she's paid full time to do astronomical research. There are folks that work in national laboratories. Um, there are, of course, folks that do things like museum work, go into teaching and whatnot. But really, the kind of training, the rigorous training in physics and mathematics and computer programming that you get as an astronomy or astrophysics major, those are what we, call transferable skills. And so there are lots of careers in industry and business and finance that somebody with training as an astronomer can also go into, and many of them pay better than being an astronomer per se. The sky's the limit, as it were. When I once was sitting down at a dinner with some members of the Board of Trustees of Ohio Wesleyan, and one of the trustees, these tend to be wealthy people who give a lot of money to the institution, he heard I was an astrophysicist and he said, "Oh, so you must just train other people to do the same thing that you do," kind of implying that there's no practical applications of this. And I said, no, that's actually not true at all. When I go to American Astronomical Society meetings, the professional meetings for astronomers in North America, uh, I will see banks and companies recruiting there with posters saying the kind of training you received as part of your astronomy degree is just what we're looking for at XYZ Corp and so forth. So sometimes it relieves parents that I talk to that their child won't only have things that they can use in astronomy, but in many, many different fields. There's another link that is in the document that I'll link to later, where there's an American Astronomical Society website, and there's a page on there that has lots of detail about the training you need to become an astronomer, and also the kind of careers that are available to folks with that training.
Fantastic. I mean, I never thought, astronomers or students who study astrophysics are able to handle large numbers. And I think that's such an important skill when you work in finance, when you work in so many fields, because uh, not even if you make a difference of 1 0, I think everything else changes. And astrophysicists and astronomers, I think numbers don't scare them, is what I
No,
feel. Yeah, yeah. And you're
they're
talking
our
about,
friends.
yeah, they're your friends, and you're talking about terabytes of data being generated through these massive, massive telescopes and the kind of technologies that you're using. So yeah, well, that's
Yeah,
interesting.
and industry uses big data too. So you learn how to use big data in astronomy, you're ready to use big data in industry as well.
Yes, yes, absolutely. So, Professor Bob, we have one final question before I invite students to ask their questions. Students, after this question, some of you will have an opportunity to post your own questions in the chat, and we'll try to take some of them. So, be ready with your questions. We would like to take as many, but with given the limitation of time, we'll try to see how many we are able to cover. Professor Bob, how can these young learners start working with real astronomical data, and what tools or experience would you recommend uh, to get started?
Yeah, so I mentioned that we're in the era of big data, and we do use computer programs and machine learning and so forth to process it, but there are still things that humans are better at than computers. And so there are a lot of what we call citizen science projects where astronomers and also researchers in other sciences solicit help from the general public in order to analyze these big data sets. So one example is Galaxy Zoo, where members of the public helped astronomers classify large numbers of galaxies. And they even discovered some unknown, unbefore seen types of galaxies in these images that they were given. The Vera Rubin Observatory is going to involve citizen scientists in processing these reams of data. Again, computers will help, but there are still things that humans are better at. And it's also just good to learn how to process data as a human. And there's a website called Zooniverse. Again, I'll have a link to it, but it's zooniverse.org, Zooniv, iverse, like in universe.org. And they have lots of projects on there where you get access to real astronomical data, and they want your help processing it. There's a web page on a magazine called Physics Today. Again, I'll have a link to it that describes Zooniverse and a lot of other projects. It's kind of targeted at teachers, but students can benefit from it too. It lists all kinds of resources where you can get your hands on real data and learn how to process it and have a lot of fun doing it.
Thank you so much for those resources and those ideas. And actually, I would like to ask one more question. What is another tip? Any other tip that you have for students who who want to build a career in astrophysics and astronomy?
Yeah, I mean, it really, in terms of how you need to prepare yourself, I think the answer is simply go to college, right? And major in astronomy or astrophysics or physics for that matter. Many folks who end up in a career in astrophysics were physics majors as undergraduates because astrophysics, there's physics in the name for a reason. You know, you're applying physics to study the universe. Um, when you're in high school, again, you don't need to do this beforehand, but certainly it's not a bad idea. Learn Python programming. Python programming is so important now in many scientific fields. Um, you can learn that in college, but if you come in already knowing it, you've got a leg up. Similarly, you can learn calculus in college. I didn't take calculus. My high school didn't offer calculus, so I took it in college. I think I turned out all right. But if you've got the opportunity to study calculus and physics in high school, um, go ahead and take those opportunities because that'll give you a head start when you get to college. Although, again, I emphasize you don't have to. I didn't take college level physics when I was in high school. I didn't take calculus. I think I ended up all right. And I do think that that page that I mentioned on the Astronomical Society website, it beautifully lays out the typical educational path of somebody who wants to go into astronomy and astrophysics. One thing I will mention that has been of great comfort to many parents that I've talked to with their prospective students when they came to visit me is that while you have to pay in the States for your undergraduate education, graduate school is free. So once you're on the way to earning your PhD in the sciences, you're actually paid to be a student. You're not going to get rich on the money, but you can readily feed and clothe and give yourself shelter with it. You're paid to be a researcher, and so your family's off the hook after that. And so I've had many students who it was a big sigh of relief for them when they realized that they were not looking at paying for, 8, 10 years of schooling for their child.
Fantastic. Thank you so much, Professor Bob. And I can see a bunch of questions coming in the chat. Let me try to pick up some of those for you. There's this one question about if which programs in Python can be used in star planet research. Do you want to pinpoint on some of those programs or?
Yeah, so there is a library of astronomical programs, AstroPython, that professional astronomers use in order to apply Python programming to their research. Um, Basically, the first step, of course, is to learn how to program in Python in the first place. And then Google searches will take you to libraries of programs that astronomers use with Python in order to further their research programs.
Okay. What is your take on the three-eye atlas that recently passed us? Like they're saying it
Yeah.
was alien, there was life, but what do you what's your take on that?
Right. So while I take very seriously the possibility that we're not the only intelligent life in the universe, as the astronomer Carl Sagan would say, extraordinary claims require extraordinary proof, right? And so the idea that it is an alien spacecraft or of intelligent construction is an extraordinary claim that would really require extraordinary proof. And so my take on it is that I really doubt that that's the case because you can explain it as a cometary or asteroidal body from another star system that wandered into our star system, wandered into our solar system. And now we have the privilege of being able to watch it fly past the sun. And I think that's probably all that there is to it, although that in and of itself is cool enough.
Fantastic. Okay, now there's this question: which upcoming space discovery do you think has the highest chance of surprising us and affecting the life on Earth?
Well, gosh, that's a big question, and I don't know that I have an answer off the top of my head for that. Um, in terms of, practical everyday life sorts of things, that's a little harder. Again, I think the main reason to study astronomy and astrophysics is to find our place in the universe. As I like to tell my students, the story of the universe is your story because you're part of the universe. And learning how stars evolve showed us, for example, that every atom in our bodies except for the hydrogen was built inside stars, and the hydrogen came out of the Big Bang. I talked to my students about how when I was in Hawaii, we went to a farm and we saw some cows on the farm, and it just dawned on me that the cows have no idea that they're on an island in the middle of a vast ocean. And I say, we shouldn't be those cows in Hawaii. As humans, we have the ability to know where we are in the universe, and we should do so. And I think in terms of big, exciting discoveries that are coming up, we have still not a good understanding, for example, of what dark energy is. It seems to be an energy associated with space itself that's causing the universe's expansion to accelerate. And we don't know yet what dark matter is. And there are active projects that are looking to answer those questions. It's interesting to note that we still don't know what most of the universe is made of. And astronomers are actively trying to determine that. And so while that's not going to affect, how people pay the rent and so forth, it will give humanity an important new piece of the big picture of how we fit into the universe. And so, if I had to pick one thing that other people are doing, not me, that I'm excited about in terms of the research, it's looking into dark matter, into dark energy,
Yeah.
and trying to find out exactly what those are.
Yes. And I think that also answers another question which was in the chat about what are some unanswered questions in astrophysics right now. Um, uh, what is the daily life of an astronomer or an astrophysicist like?
Yeah. So one thing I'll say is I have colleagues, I have other professors who sometimes imagine that I'm always going out to a telescope, that I spend half my nights at a telescope. Um, and in fact, that's not the way it works because the large observatories, I mean, one thing nice is there is an observatory on campus that I get students involved in hands-on projects in, but in terms of like large observatories, right? The space observatories, big telescopes on mountaintops like Vera Rubin and so forth. There's not there, that's a resource where astronomers will put in proposals who are observational astronomers to have observations made with telescopes like that. And so an observational astronomer might get a few nights of data a year from a large observatory telescope like that. And then they spend the rest of their time analyzing that data. So that's one misconception people have is that astronomers are always going to telescopes. That's actually not the case. You spend a lot more time talking to students and analyzing data than you do collecting the data. Um, and also, it depends on what kind of astronomer you are. So, for example, at Ohio Wesleyan, we emphasize teaching. Research is very important to me, but I love teaching. I love spreading knowledge and exciting students and so forth. And so, a lot of my daily life is teaching and preparing to teach and giving talks and stuff like that. People that work at national labs, their day-to-day is more analyzing data or building instruments and things like that. So I think the big picture is that astronomy is typically more of a 9 to 5 job than people might imagine, as opposed to you're spending all your nights at the telescope. It doesn't work that way.
Yeah, yeah. It's what I see is, I mean, in my limited knowledge, you use the telescope, and that's what you said, use the telescope for some time and then come back to your systems and analyze that data, understand that data,
Yep.
make sense of that data, and then go back to sort of uh, create your hypotheses and then again bring back some more data and then work on it again, maybe.
Yep.
Yeah. Yeah.
Yes. Hmm.
Okay. So, a couple more very interesting questions. One is about what evidence is there to support the Big Bang theory, and the second one is what is your opinion on the theory of multiple universes, whichever
Uh,
one you want to talk about, and if you want to talk about both of them.
right. So there is a lot of evidence that supports the Big Bang theory. It's pretty much undeniable that the universe was much hotter and denser in the past than it is now because we can see for ourselves. We can measure the motion of galaxies, and we find systematically that they're getting further away from us, and that the further away a galaxy is from us, the faster it's moving away from us. And according to general relativity, that's a natural consequence of how the universe works. It's a prediction of general relativity that space expands. It could be contracting or expanding. The observations show that it's expanding. Distant galaxies move away from us faster because there's more space expanding between us and them than there is between us and a closer galaxy. So we know the universe is expanding. It's not a stretch of the imagination to run the clock backwards and everything gets closer and closer together. The wavelengths of photons, light particles traveling through the universe, get longer and longer. In reality, as the universe expands, they get shorter and shorter if you run the clock backwards. Most of the photons in the universe are from a time about 380,000 years after the Big Bang, when the temperature had cooled to the point where the first atoms could form. And we understand physics well enough to sort of run time backwards to about 1/10 billionth of a second after the Big Bang. After that, we need better theories to fully understand what's going on. But just the idea that the universe was much hotter and denser and everything was much closer in the past, that's pretty much unassailable. The details are up for vigorous discussion among scientists, but that's pretty much unassailable. One of the biggest pieces of evidence for the Big Bang idea is that we can calculate when the universe was a few minutes old, hydrogen would have fused into helium, and we can use our understanding of physics and extrapolate back to the conditions that would exist back then and predict that the universe should be about, in terms of its ordinary matter content, 25% hydrogen, helium by mass today, 75% hydrogen roughly. That's exactly what we can see. We can account for other rarer isotopes as well. There are just, I can't get into them all here, but there are many lines of evidence in favor of the idea that there was the Big Bang. In terms of multiverses, that's very speculative. For what
Mhm.
it's worth, I personally, I'm not going to bet the rent money on this. I personally suspect that there is a multiverse. I personally suspect that our universe is a bubble in a background that is constantly undergoing what we call inflation. And quantum field theory can be used to argue that there could be transitions that cause little regions to stop expanding so rapidly, and those regions could become universes. And I suspect that's what's going on, but we don't have any direct evidence for that.
Wow. Fantastic. That's fascinating, actually, and sounds a little bit like fiction. But yes, I think
It
that's
does.
all. Yeah. So,
It
yeah.
does. I tell my students that, it might sound like the cosmologists have been smoking something, but believe it or not, there's rigorous mathematics and
Yeah.
physics that we apply to all of this.
Super. It is so much fun, Professor Bob, having you with us here today. And we are almost coming towards the end of the session. Any final piece of advice or any final words for these high schoolers? These are all 14 to 16-year olds, in their high school, junior, sophomore years, anything that you would like to share with them yeah.
Yeah, I guess I would just say that when I was in high school, I had a guidance counselor who said something. It wasn't to me, it was to a whole class, that has always stuck with me, which is that happiness isn't doing what you like to do, it is liking what you have to do. In other words, we all have to make a living, we all have to earn money. And you want it to be in a way that you enjoy if you can make that happen, right? In other words, you make a lot, there are jobs, and I'm not saying nobody should take these jobs, but you should try not to have a job where all you think about is how much money you make. Yeah, I want to make as much money as I can too, right? But having a lot of money lets you do things like take vacations and so forth. But if you don't like what you're doing, is it really worth it? Right? If you can find something, be it astronomy or anything else, there are so many things that can fit this definition. If you can find something where you actually enjoy what you're doing as a career, I think that really is the key to happiness, right? I don't like every aspect of my job. I wish papers would grade themselves. It's very tedious and so forth. But nevertheless, I really like what I'm doing. I wouldn't trade it for anything. And that's something that I hope all of you can achieve for yourself someday.
Wow, that's amazing, and that's the best time to stop. I think happiness is not. Can you come again,
Yeah,
please?
happiness is not um, doing what you like to do, i.e., in other words, taking vacations and so on and so forth. Um, Happiness is liking what you have to do, right? You have to have a career and you want it to be something that you like, as opposed to something that you dread just in order to be able to afford to do other things that you actually like to do.
Wonderful, wonderful. Thank you so much, Professor Bob. And may I request you to share the links that you
Yes.
had referred to, so
Yep,
that
I
students
just
can
did.
make
I just
note of
put
that?
a link to the document, which itself has links to other resources. I saw so many good questions flying by in the chat. Of course, I don't have time to answer them all, and I couldn't get them all super quickly. But if the chat is saved afterwards, and if I can get a hold of that, I can try to answer questions over time, because I feel bad that I see all these wonderful questions and we didn't have time to get to them.
I will certainly send these across to you. But if there is any particular question that you would like to take up, we have a couple of minutes, and if you do have a couple of minutes, please feel free to pick up the questions that you really want to address.
Well, there's so many of them. I just saw many, and so there's, I'm like, wow, and I just know there's more. Here's just one sort of I'll pick at random. As an avid stargazer, I have looked for resources online on how astronomers determine the distance between us and the stars. How do they measure it? So, um, when we look with our two eyes, if you hold your thumb out in front of you and blink your eyes back and forth, you'll see that your thumb is in front of different things. That's called parallax. And without you even thinking about it, your brain uses the images from your two retinas to look for parallax, and that's what gives you your depth perception. Stars are much too far away for that to work, but on the other hand, we're riding on a spaceship called Earth that goes around the sun. And so, what astronomers do fundamentally to accurately determine stellar distances is to compare images of star fields taken in different parts of Earth's orbit and noticing very slight shifts of nearby stars' locations on the images compared to much more distant stars, which hardly move. And we can do the same thing that our brain is doing with our two eyes. We can do a little bit of trigonometry to determine how far away those stars are. And that's the basis for stellar distance determinations. And then for other things like galaxies, which are much too far away for parallax, we use what are called standard candles. In other words, stars which are very luminous and which we've been able to know what their luminosity is from other characteristics, uh, and for which we can determine distances of nearby examples using parallax. And so we have what we've called the distance ladder in order to find more and more distant objects in the universe, how far away they are from us. So that's just one example of the many questions here that I see.
Superb, superb. Thank you so much once again, Professor Bob. I really thoroughly enjoyed having this conversation with you, and I'm sure the students are thrilled as well. And I can see that many of them are going to use the resources that you have shared, and it was inspiring. So I'm truly grateful to have had this opportunity of speaking with you today.
I'm grateful that you invited me. I've really enjoyed it. It's really wonderful to see so many people who are interested in the same things that I'm interested in.
Absolutely. And I hope some of these will get a chance to study and to sort of come to OVU and actually get to work with you in person.
I'd certainly be happy to have that. And I'm willing if folks reach out to me to set up a Zoom meeting to talk about Ohio Wesleyan. I wouldn't have time to just chat about astronomy in general. Oh, it's overwhelming. But if you're interested in Ohio Wesleyan in particular, I'd be happy to meet and talk more about it.